In the first setting, we did go through a lot of stuff actually, covering up to the unconstrained optimization. Starting from now, we will talk about constrained optimization step by step. In this session, or this part, will cover dedicated this lecture, and it's already on the main slides, 4 optimization problems in 2 main variables subject to 1 equality constraints. So, first of all, we talk about the unconstrained inequalities, optimality, and we did go through the various steps by finding the main function, making the derivatives, getting the Hessians, blah, 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 above, in details about everything. Now, for the time being, we will discuss a more critical case, which is the case of discussing the optimality of a certain optimization or certain optimal function, but with 1 constraint, which is an equality constraint, I'm sorry. What's an optimization problem? This is the problem of 2 inequality constraints, as I told you. Let's study one of the most well-known problems. This problem is discussed in general and in details the consumer problem, which in which the consumer wants to maximize the utility, the maximum use of his budget, but unfortunately his budget is limited to a certain value. So it's a case of getting the optimum solution, but under 1 condition, which is a condition of a limited budget. In general, for any optimization problem, in this case, we will go through the following. This is the objective function, which is going to be subject to maximality or minimality. Maximizing in the case of profit, revenue, blah, blah, blah. Minimizing in the case of effort, in case of expenditures, and so on. Subject to this group of constraints. Usually the constraints try to identify the visible area of solution or to determine a specific area of solution. So in general, we would like to find the best solution for a set of visible solutions that's satisfying the equality set of constraints, and the number of decision variables must be the number of decision variables, we mean x1, x2, x3, or x, y, and z, must be greater than the number of constraints in order to make certain flexibility or alternatives in order to gain our solution. The graphical representation will be available for some problems in case of an optimization with 2 decision variables and 1 constraint. It is possible to have a graphical solution. This is the shape of the function, and that's the equality constraint that we are talking about. So the procedure is like this. First of all, identify the visible region or the subset of R2 with the solutions that's satisfying the constraint. Let's present the set of all solutions that satisfy the constraint of the problem. Number 2, identify the level curve of the objective function. يبقى لو أنا بعمل graphical solution mainly بمسك الconstraint بحاول to identify an area of this constraint or the part of the straight line of this constraint, and then وده بيطلق عليه السولوشن set. بعدين بجيب الليفل كيرف وهو ال represent الobjective function. Optimality will happen once they will be tangent to each other. Then the general expression for the level curves should be identified. Identify the optimal solution. Finally, with the help of the level curves and the visible area of solution, we will be able to find the best solution for the objective function satisfying this constraint. We have more than 1 method to analytically solve the case of optimality with 1 constraint. The first of them is the implicit substitution method, and this is really very nice method. I have function f of x, y. I have the constraint, which is g. The idea behind the implicit function theory is at the optimal solution, the derivative or the implicit derivative of the objective function will equal the implicit derivative of the constraint. And that's the key to find our optimal solution. So if you remark at the optimal solution, the level curve of the objective function is tangent to the constraint. That means their partial derivatives equal to each other. And it is written here too, if both the objective function and the constraints are differentiable function, then at the extremum point, the slope of the two functions defined by the level curve and the set of solution will be equal to each other. That's mainly the main key. I will skip all of these steps. Already we did go through the implicit definition. So if I want to get dy by dx for any function, for an objective function or so, all I have to do is to get partial f partial x divided by partial f partial y with the general conditions that we discussed previously with a negative sign. I will do this for both the objective function and the constraint. At the optimality point, these two guys should be equal to each other. You will find this in this slide. So that's the implicit derivative for the objective function. That's the implicit derivative of the constraint that we have. At the optimality point, they will be equal to each other. So together, this condition with the constraint, I will be able to get my optimal solution. So once more, for the cases of optimality with one constraint, I can find the solution by graphical method. The graphical method, just only I've given a summary for it. All I have to do is to graph the objective function, graph the visible area of solution. The point at which the maximum will happen can be determined by getting the objective at the end of the visible area of solution. Okay, we will go through the analytic methods that more convenient for our analysis. The first of them is the implicit method or the implicit function method. It's really very simple. You will have for each optimality problem in this type, you will have two equations. One of them or two expressions. The first of them is the objective function. The second is the constraint. Get the implicit derivative for both of them. Put it equal to each other. You will have an equation. Use this equation together with the constraint and you will be able to get your extremum point. The point of optimality as an equation. So if, for example, if I have this example, he is giving you the optimality function, or you need to discuss the optimality function for x plus y subject to this constraint. So if I want to solve it, the first step that I will do, I will take this function, which is the objective function, getting the implicit derivative, which is really very simple. So all I have to do is to get the objective function, okay, partial x, for example. So all I have to do is to get the derivative of x, which is gonna be 1, divided by the partial derivative for the objective function with respect to y, it's gonna be 1, with a negative sign. That's the implicit function theory application for f of x and y. Getting dy by dx. So actually, that's the dy by dx for the objective function. I will do the same, also getting the dy by dx, but from the constraint that we have, which is x squared plus y squared equal to 4, which is very, very simple. Differentiating with respect to x will devote 2 of an x. Differentiating with respect to y, it's gonna be 2y, of course, with negative sign. And yes, you are right about this constraint. Here it will make no difference, but it should be like this: x squared plus y squared minus 4 equal to 0. Same way for the upper objective function, but the objective function is just the function, so you are not going to find a left-hand side and right-hand side. It's going to be the function by itself. Just get dy by dx, which represents the slope of the objective function. For the second function, it's supposed to be on this form. Here it will make no difference. But if I have 4y, for example, it will make a difference. But for here, it will make no difference, getting dy by dx. putting them equal to each other, this is what happens at the optimality point. So at the optimality point, you will have 1 equal to x over y, assuming we cancel these two guys, which is going to lead to x is equal to 1. So now I have x equal to what? To 1. For the time being, I have this condition which states that x is equal to 1. This is number 1. The number 1, x plus 1. I will use it with the constraint equation, which is x squared plus y squared equal to 4. Okay, how we are going to use it? Make a substitution from this guy into that guy, which means I will have x squared plus x squared equal to 4. That's x squared is equal to 2, which is gonna give x is equal to positive or negative root 2. Now I know the value of x at which the optimality point will happen. So using this information, I can get also y, which is going to be positive or negative root 2, exactly the same. Now I have the optimality point. This is what's stated here. Using the implicit function theory, I will get the derivative of the objective function, make it equal to the derivative of the constraint. From these two guys, I will have a relation connecting these two variables. I will use it and substitute in the constraint. Then from this, I will get the points of optimality that I'm searching in, which will be an optimal value for the function and also satisfying the constraint given. You understand what I'm saying? And this is mainly or simply the implicit function theory. It's very good, and it can handle functions in two variables very easy, especially with one constraint. Okay, so this is one of the methods that we can use. Okay, this is the implicit function solution, as I told you in details. The second method is the substitution method. And this is very nice. All I have to do is to use the constraint to make a substitution in the objective function. And once we do so, we will have an unconstrained function. So the second method, substitution method, الميثود دي بتعمل ايه؟ هتخلي optimality with equality constraint to be an optimality function with no constraints. هترجعني زي ما كنت بعمل قبل كده. اجيب الفيرست ديريفيتيف سكند ديريفيتيف وامشي بالبروسيجرز. بص ازاي بنعملها. هنا مثلا فور اكزامبل انا عندي f of xy which is x plus y وعندي هنا x square y square equal to 4. The main idea is to try to make the substitution as I told you. I will just decrease these steps. I will use the constraint. Constraint عندي x square plus y square equal to كام؟ To 4. Get y as a function in x. So it's going to be 4 minus x squared. Taking square root for both sides, you will get the value of y, satisfying the constraint. I will use it and then make a substitution in the objective function. Now I regained to the unconstrained optimality part. So the idea is to substitute by the constraint into the objective function to have one variable as a function in the other variable, which will reduce the problem to be a variable unconstrained problem. يبقى أنا عندي implicit function theory أو implicit function theory, which is really very simple. Get the derivative of the objective function, derivative of the constraint, make them equal to each other. Use this equation or this information together with the constraint, you will be able to get your optimality point. This is method number 1 in analysis. The second method is exactly the same, or I'm sorry, not exactly the same. It's gonna reduce the problem of equality constraint into the problem of unconstrained optimality. How to do this? We will make a substitution using the constraint equation and make the substitution in the main function, and so we will be able to deal with it. So هنا مثلا على سبيل المثال, it's really very simple. All I have to do is to get y squared equal to 4 minus x squared, which is going to develop y equal to positive or negative a square root for 4 minus x squared, taking this condition into the objective function. So my new objective function will be simply x plus or minus a root for 4 minus x squared, and then I will start my analysis for these two functions. Once was positive, once was negative, according to the previous steps that we take. Get the first derivative, put it equal to 0, get the critical points, get f double dash, make the substitution, discuss according to the second derivative rule. If it is maximization, minimization, you will be able to know all of this. So that's mainly the second method, as you can see. In the case of constraint or optimality problems with constraints, so it's exactly y getting positive or negative 4 minus x squared. I will have for y greater than 0, I will take the positive side. For y less than 0, I will take the negative sides. So I have objective function, two objective functions, and they will continue my analysis. Okay, constraint optimization. This is part 2 or the second part, and it will be dedicated for the constraint optimization with one inequality constraint. We will study the suitable method to analyze. Okay, that's the introduction for the Lagrange multiplier method. The Lagrange multiplier method is one of the very successful methods in treating the problems in general, and the most famous one with equality constraint. It's really very simple. All I have to do is to form the Lagrangian function and then differentiating it with respect to its variables, putting them into equal to 0, then solve the system and getting the critical points, and so you can continue your analysis. It's really very simple. Okay? So the introduction and also the Lagrangian method, it will be used in the inequality constraints, as we will see down just in a few. So the Lagrangian multipliers method is a technique used in constraint optimization. That's to find the maximum minimum of a function subject to an equality constraint. That's the introduction. We'll find the details of this method with everything in the slides. This is the Lagrangian function that I need you to take a good look for it. That's what we mean by Lagrangian function. This is the objective function. That's lambda, which is greater than 0, times the constraint, b minus x and y. So if I have, like the previous problem, for example, the objective function is x plus y, and the constraint is x squared plus y squared equal to 4 or something. So all I have to do, if I want to write the Lagrangian function, L, it's gonna equal to, this is the objective function, معايا دينا؟ الكلام ده plus lambda times, بصي, move x squared plus y squared into this side. So it's gonna be 4 minus x squared minus y squared. That's the Lagrangian function. Then start the analysis by differentiating this function with respect to its main variables. هو مين decision variables هنا؟ x and y. لذلك هروح رايح جاي partial L partial x وput it into 0. partial L partial y وput it into 0. تعالي نعمل ده واحاول اsolve التو equations دول مع بعض together مع الكونديشن اللي already exist معايا اللي هو x square plus y square equal to 4 or whatever. يبقى انا لو بدات اعمل كده اول حاجه derivative with respect to x هيديني 1, it's gonna be a 1 minus a 2 lambda of x equal to 0. Same way for y, it's gonna be 1 minus 2, am I right? It's right? Lambda of y, which equal to 0. From these two guys, I can get lambda, which is gonna be, okay, 2 lambda of x, which is gonna equal to 1, which leads to lambda equal to 1 over 2x. Are you with me, princess? The second one is gonna be 2 lambda of y equal 1, which leads to lambda equal to 1 over 2y. From these two guys, Lambda lambda would say 1 over 2x, 1 over 2y. So that means in 1 over 2x is equal to 1 over 2y. That's y equal to x. Once you have y equal to x, I will use it in the substitution of x squared plus y squared, and I will get similar result to what I have previously. So now we know that we have the three methods: the implicit function, the substitution method, and then the Lagrange. In the implicit function theory, all I have to do, get the dy by dx from the objective function, get dy by dx from the constraint, put them equal to each other, you will have a relation together with x squared or with the constraint, whatever it is, you will be able to get your optimal points. This is method number one. Method number two, all I have to do is using the advantage from the constraint to get y as a function in x. Use this advantage and substitute in the objective function. Then you will treat your problem as an unconstrained problem, as we used to do in the previous part of this session. The third method is to get first Lagrangian method, which is really Lagrangian function, which is really very simple. It's simply the objective function plus some lambda, which is greater than 0, times use or the condition that's given to be b minus g of xy. So it's going to be a 4 minus x squared minus y squared. Now I have the Lagrangian differentiate at with respect to its variables, partial. So I will differentiate L with respect to x, L with respect to y, putting them together equal to zeros. Then I will be able to get the critical relation connecting x and y. Using it with the condition, you will get the critical points. Exactly like the first method. Okay? حلو قوي. ده Lagrangian method. It's an introduction, and we will use it with the system of inequality constraints as used. So it's very, very simple. And it is applicable with if you have more than one constraint, equality constraint. Maybe I will have, in some problems, once you try to formulate, you will have 3 or 4 equality constraints. So you will be able to generalize this method. Of course, all the steps are the same. Getting h dash, which means the derivative of the Lagrangian function, equal to 0 based on the derivative, study the sign, blah, blah, blah. Of course, these are just an introduction for getting the value of lambda. And this is going to be the border Hessian matrix in case of multi-variable functions, which I will depend on it in determining the case of the Lagrangian, if it is maximum or minimum and so on. Okay? So it's really easy, and you will find the details in the main slides. So I don't want to spend more time in these slides. For the n variables in n constraints, I can, as I told you, generalize the method that I said previously about the Lagrangian function. I'm just searching for, here we go. That's the Lagrangian function for an objective function with not just only one constraint, but more than one constraint. All I have to do is write the objective function, getting the lambda 1 times the first constraint, lambda 2 plus these times the second constraint, and so on. So it can be generalized, very simple, relative to what we saw, and then we will try to differentiate the Lagrange function with respect to its main variables, getting a system of equations, trying to solve them together with the inequalities, with the equality constraints that exist. You will be able to identify the critical points. Just a generalization. Consider now the border Hessian matrix, which is going to be n by n. It's continuation of how to get the minimum and the maximum, exactly like what we discussed in the case of one constraint with the Lagrangian method. This is the envelope theorem, or the envelope theory. Once the version of the theory when we have an equality constraint. وموضوع الانفلوب فانكشن هنا بالظبط قايم على اللاجرانجيان. يعني اذا الفيرست ستيب انك تجيت اللاجرانجيان فانكشن. لاجرانجيان فانكشن بتكونكت مين بمين؟ زي انت واخده بالك. عشان اجريت بسرعه شويه خلال الفتره اللي فاتت. فيرست اوف اول انا بجيب اللاجرانجيان فانكشن. لاجرانجيان فانكشن هتقدر تحدد لك الاوبتيمال بوينت عن طريق انك تسولف السيستم مع الكونسترين الموجود. جبت الاوبتيماليتي بوينتس، هعمل ايه؟ هجيب الهيزيان ماتريكس بس بتاع اللاجرانجيان فانكشن. بالتالي بيطلع derivative with respect to lambda, derivatives with respect to x and y. فبالتالي لو انا عندي one function in two variables هيبقى عندي هيزيان 3 في 3. الفيرست رو والفيرست كولوم it's related to lambda الفاريبل الجديد اللي انت حطيتيه، فمش بستخدمه. لكن لو عندي ال 2 باي 2 اللي موجودين ال 2 رو او السكند رو والثيرد رو هيبقى فيهم الديريفاتيف with respect to x اللي هو الهيسيان ماتريكس اللي انت متعوده عليه. بيزد عليه اقدر تو كلاسيفاي اف انا عندي مينيمم او عندي مين؟ ماكسيمم. تمام؟ نفس اللي انا قلته ده كان بي جنرالايزد لو انا عندي مور ذان 1 مين؟ كونسترينت. طيب خلاص خلصت بقى من الجزء ده. انا دلوقتي بتكلم على الانفلوب ثيوري. الانفلوب ثيوري فاكره كانت بتعمل ايه؟ كان بنعمل ايه في الانفلوب ثيوري؟ بندiscuss the change in the optimal solution. Once there is a change in one of the parameters already exist in the objective function. نفس الكلام بالظبط. بس انا هقدر اعمله دلوقتي عن طريق مين؟ لاجرانجيان فانكشن. طيب اشمعنى؟ لان المره اللي فاتت انا كنت بستخدم الانفلوب ثيوري في الانكونستريند اوبتيماليتي، ما عنديش كونسترينتس. لكن دلوقتي ظهر عندي كونسترينت، فمحتاج فانكشن تو كونكت الاوبجكتيف زائد مين؟ الكونسترينت. مين اللي بتعمل ده؟ او مين بيعمل ده؟ لاجرانجيان. لان انت لو تخلي بالك لو فاكره يعني واحنا بنتكلم حالا كان لاجرانجيان فانكشن اوف لامدا واكس واي، او خلينا اكتبها احسن اكس واي ولامدا عشان البوينتس بتطلع كده اكس واي اند لامدا. كان بتساوي ايه؟ كان بتساوي الاوبجكتيف فانكشن زائد لامدا الاوبجكتيف فانكشن بلس لامدا تايمز بي ماينس جي اوف اكس واي. ده الجزء الخاص بالكونسترين. معايا جميل؟ يبقى انا لو عندي certain parameter ده كان already exist في الاوبجكتيف فانكشن، دي المين رول او المين فانكشن اللي كونكتنج الديسيجن فاريبلز بالبارامتر بتاعي. يبقى انا لو عملت ديريفاتيف لو هقدر ابلاي الاوبجكتيف الانفلوب ثيوري الانفلوب فانكشن ثيوري زي ما انا عملت قبل كده to discuss the changes on the optimal solution. فهنا بيقول اهو let alpha 1 up to alpha b be a vector of parameters. If one of the parameters change, what's the change that will happen in the optimal function? Exactly like previously. So the envelope theorem states that the change in the optimal function due to the change of one of the parameters, it is measured by the derivative of the Lagrangian function. Then I study the Lagrangian function and now connecting the objective will constant. Okay? With respect to the parameter at the ultimate point. نفس اللي احنا عملناه قبل كده بالظبط، بس بدل ما بعمله مع الاوبجكتيف فانكشن هعمله مع اللاجرانجيان فانكشن. طبعا اقدر استخدمه بنفس الاسلوب واقدر اوجد الفاليو استخدم الايكويشن اللي احنا شفناها. Now introduction to optimization with inequality constraints. في الجزء ده احنا we will talk about optimalities with less than or equal constraints or greater than or equal constraints, which is the general case in dealing with constraints in general. بس قبل ما ادخل فيه عايز اتكلم على 3 cases احنا we went through the third one. First of all, I'm discussing the case of optimality with no constraints. Unconstrained optimality. This is the part that we get the function, get the first derivative, insert it to 0, get the Hessian with all the details. If the Hessian is equal to 0, the first non-null derivative, everything. Positive, definite, semi-definite, or everything. It's already related to this part. The second part is discussing the optimality once I have equality constraint. And in this part, we have how many methods? 3 methods that we stated just in a second. The implicit function theory, the substitution method, and the Lagrange method. This is number 2 type. Number 3 type, which is the last type, and the more general one, is discussing the optimality function under an inequality constraints. So I will start to see constraints with less than or equal, greater than or equal, or a max between them and the equality constraints. So that's the most generalized answer. So this is the third type of optimization problem that we will take. The inequality constraints, which is the best fit to our daily life problems. ده فعلا اللي احنا بنشوفه في حياتنا. واقرب ما يكون لامثله كتير يعني. طبعا كان المفروض ان احنا ناخد linear programming الاول. انا from my point of view حاسس ان هو كان هيساعدنا جدا انك تفهم برضو يكمل الصوره يعني. بس استخدامه او استخدام النون لينير برضو it's a good idea. هنا بيقول for example if we have just only $20 and we want to buy some bread and cheese, we must carefully choose the best combination between the bread and the cheese to be within maximum to spend the $20. If I can buy what I need, what satisfy me from bread and cheese, but less than 20 will be welcome. But the maximum is less than or equal to 20. I can't go buying bread and cheese greater than $20 because I don't have them. Okay, so that's an example for just only a scenario about this. Okay, we will see some basic concepts and explore how it could be solved graphically. ده graphical method الأولاني أو first graphical method for trying to analyze the case of an inequality constraints. You will find it described in details in the main slides. And also I will talk about them. The last thing is the Karush-Tucker condition, or the KKT conditions. And the previous 2 lectures mainly was dedicated for this topic. How to get the Karush-Tucker conditions, how to solve these inequality and equations together. So it's really very important to watch them. Okay? We will prepare the analytical resolution involving the Tucker conditions later. طيب شكل الاوبتمايزيشن بروبلم بص بقى برنسس دينا شكل الاوبتمايزيشن بروبلم in this case بيبقى شكله عامل ازاي؟ This is my optimality problem, which is going to be a function controlling the decision variables x1, x2, and so on. Subject to these are some of the types of the inequality constraints that you will face. The first bunch of them is non-negativity constraints. The non-negativity constraints, as you know, are the constraints that spot to control the nature of the decision variables. أنا عندي متغيرات باخد فيها قرار زي x وزي y. الاكس والواي دول لو حاجة أنا بمسكها بإيديا أو بريديوسد أو بعمل بيها أي حاجة محسوسة لازم تبقى الأرقام دي بالموجب. يعني مثلا على سبيل المثال we are a restaurant serving burgers and hot dogs. The number of burgers will be served is x. The number of hot dogs that will be served is y. Okay? يبقى أنا عندي 2 decision variables. Number of burgers, number of hot dogs. أبسط حاجة to maximize my profit or to maximize my income as a restaurant. صح؟ يبقى how many decision variables? 2, which is x and y. The first inequality or the first inequality constraints. X is greater than or equal to 0 and y also is greater than or equal to 0. It makes sense. ليه؟ لأن the number of sandwiches that you will make must be a positive number. Is it gonna be possible to be a negative number? No. This is why you have non-negativity constraints. But then there are a lot of inequality constraints. Like for example, أنا ما عنديش النهاردة إلا 40 باتيه. for burgers. يبقى ما اقدرش اعمل الا 40 ساندوتش. يبقى X must be great less than or equal to كام؟ to 40 patties. Hot dogs I have up to 200. يبقى Y is less than or equal 200. You understand what I'm saying? The people usually from my previous study, the production or the demand on my sandwiches, it is limited to 300 sandwich per day. يبقى ده معناه ان X plus Y هيكونوا اقل من او يساوي كام؟ 300. Do you understand what I'm saying? يبقى هنا عملت الترمينولوجي. It makes sense ان inequalities اللي موجوده عندي greater than or equal, less than or equal. The negative signs will appear in directions like the cash flow. The money in is going to be a positive, the money out is going to be a negative money. If I'm making a model about movement or cash flow of money, okay? معايا جميل؟ اوكي. طيب لو انا عندي optimization problem، اول حاجه الاوبتمايزيشن تايب. Is it minimization or maximization؟ هنا انا بطلب عليك I need to minimize, I need to maximize. So I need to minimize this function under the set of these constraints. I need to maximize this function under the set of these constraints. So the optimization function will be the objective function. Usually find the extremum points and the extremum values. The decision variables are x1, x2 up to xn. These are the decision variables. Okay. Usually there is parameters or other parameters may appear. يعني مثلا لو انا قلت لك my income for the restaurant example that I told you about, I'm gonna sell the hamburger or the burger sandwich for $5, and the hot dogs or the hot dog sandwich for $2 or $2. لذلك لو انت جيتي to formulate the revenue function هتبقى 5 times x plus 2 times y. Am I right? صح? It makes sense. 5 times x, $5 is the price, times x, the number of burgers, plus 2 is the price, times y, the number of hot dog sandwiches. So the objective function in this case will be 5x